Hello everyone. In our last lecture, we talked about Coulomb's law, which is the electrostatic force F of C. This is equal to K Q1 Q2 divided by D square. Here Q1 charge, another charge Q2, they are at a distance D, and this is the Coulomb's law. The electrostatic force between two charged objects is directly proportional to the product of the charges. This is Q1 times Q2, and inversely proportional to the square of the distance between two charged particles. Okay, and here K is the Coulomb constant, proportionality constant, and this is approximately equal to 9 times 10 to the power 9 Newton meter square per Coulomb square. This is a Coulomb force, and we also talk about the electric field. Which is a vector quantity. This the Coulomb force. This is also vector quantity. Let us suppose if you have a charge Q here, we call this is source charge, then you can feel the effect of this charge around here, this area. You can feel the effect of this charge. You can experience the effect of this charge. And in this area, I want to choose one point here. For example, this point. This point is P, and this is at a distance, let's say, R. Point P is at a distance R from the source charge. This charge we call source charge, and this is right here. I want to keep little tiny charge Q0. We call this is test charge. It is really tiny, and the electric field is defined as electric field E. This is a vector quantity. This is equal to force, electrostatic force per unit charge. This is what we call the electric field. Okay, and this is, electric force is Newton and charge is in Coulomb. Newton per Coulomb. That is the unit of electric field. Again, don't forget, electric field is a vector quantity. Okay, so we already discussed about this in our last lecture. Today I want to talk about the electric lines of force. Electric lines of force. Okay, let us suppose you have a charge. Let's say this is a positive charge, and you have another charge here, negative charge. They are at a certain distance. Okay, you can see the distance between them. If this charge is equal in magnitude, these two charges, if Q1, let us consider this is Q1, this is Q2, if they are equal and opposite charge, you keep at a certain distance. That is called as the electric dipole. Okay, so if this Q1 is equal to Q2 in magnitude and they are at a certain distance, we call that electric dipole. Now look at this. If you bring one really tiny charge right here, this is really small charge, tiny, very small charge. What happened? This positive charge repel this test charge, tiny charge, because we know that like charge they repel. So what happens? Simply this charge follows this path. It go there. This tiny charge, this charge goes here toward the negative charge. So this is the path followed by this test charge, or you can call tiny, really small charge. And this path is we call electric line of force. Path followed by the test charge in that electric field. That is called as the electric lines of force. So you can draw the several electric lines of force, as many as you want. So one electric lines of force, you can draw as many as you want. So this is electric lines of force. Another electric lines of force you can draw this way. This is also electric lines of force. This one, this is also electric lines of force. Okay, so the electric lines of force start from positive charge and terminate at the negative charge. This is the first point. Electric lines of force start from positive charge and terminate at the negative charge. Okay, so I already mentioned that if you want, you can draw many electric lines of force like this. Even if you want, you can draw this way. Don't forget to give the arrow, and here you can draw like this. Okay, so these are the electric lines of force, and you see two charges, plus and minus, equal charge, opposite charge. This is electric dipole. But if you have just the positive charge, this, how do you draw the electric lines of force? Just simply you can draw this way. Electric lines of force start from positive charge. So the electric lines of force is outward like this. This. If you have just the single charge, I mean the positive charge only. So where is the negative charge? Somewhere. We don't know, but this line goes somewhere where it gets the negative charge there. So we call, if you have just one charge, we call monopole. Similarly, if you have, like, let us suppose if you have a negative charge, then how do you draw? If you have this, then you do the same thing, but the arrow is different. Inward. This is how you draw the electric lines of force, and this is also the monopole. And I already mentioned that electric lines of force start from the positive charge and terminate at the negative charge, and that is the first property. And the second property is suppose you have again the same, it is the same diagram. So this is your electric lines of force. Suppose this is your electric lines of force, and you can give the arrow. If you draw the tangent at this point right here, any point, you can choose any point, but I choose this point, and if you draw the tangent like this tangent right here, let me call point X or whatever, at this point, if you draw the tangent, okay, this tangent gives you the electric field right here at this point. So the second point is the tangent drawn at any point on electric lines of force gives electric field at that point. Second property. So if you draw another line, for example, let us suppose you have a set line this, and if you draw the tangent here like this, so this is this tangent, this one, this gives you the electric field at this point. So this is the second property. And third property is, okay, if you have again charge here, negative charge there, one electric line of force is this. And if you draw the another electric line of force this way, Look, these two electric lines of force, they intersect here. Two electric lines of force, they intersect here. Okay, but this is not possible. Two or more than two electric lines of force, they do not intersect to each other. This is not correct. Okay, so why? Right here you have a two curve, they intersect right here. So you have a two tangent here. One is this, okay, another one is this. That means you have a two electric field, two vectors there. That is not possible. Okay, so your third property is two or more than two electric lines of force never intersect to each other. This is not possible. Why? Because at the point of intersection you will have a two electric field. That is not possible. So this is the third property, and these three properties are really important, but there are many properties. For example, you can see the electric lines of force, they are crowded, concentrated near the charge. Like, let me draw one more time. You can draw like this. The electric lines of force, they are crowded here near the charge. That means the electric field near the charge is more. If you move far, move far, they like scattered. So electric lines of force, they are crowded, concentrated near the charged particles. Okay, you can make that another property. And similarly, if you want to draw the electric lines of force, like let us suppose this is the charged object, the electric lines of force, they are always normally coming out of the, like if this is a conductor, they are right here, it is 90 degrees, this way. Okay, so this is about the electric lines of force. Then the electric lines of force, we also call as the electric flux. Okay, electric flux, we simply use phi to represent the electric flux. This is phi, okay? This is phi. So let us suppose this is the area, certain area, surface area here, this, and consider this is a electric field, okay, and right here, this is the line. This line is perpendicular on the surface, this area. Like if this is the surface, the dash line is perpendicular to the surface. Perpendicular to the surface, not perpendicular to the electric field, perpendicular to the surface. And let us consider this angle is theta. Okay, the area of this surface is A. So what is theta? Theta is the angle between the direction of electric field and the line drawn perpendicular to the surface area. This line, the dashed line, is perpendicular to this surface. And here I would like to define electric flux. What is electric flux? Electric flux is, it is electric lines of force, number of electric lines of force per unit area passing through the area perpendicularly. So how many electric lines of force passing through this area, this surface area? But the electric lines of force and the surface area, they must be perpendicular to each other like this. If this is your surface area, and how many lines passing perpendicularly through this surface area, that is what we call the electric flux. And the formula to calculate the electric flux is phi, this is how we represent the electric flux. This is equal to E is the electric field, A cosine theta. What is theta? Theta is this angle. Theta is this angle, the angle made by the line drawn on the surface of the on this surface area, and which is perpendicular to the surface. So the angle between the electric field, direction of the electric field, and the line perpendicular to the surface area, that angle is the theta here. And if this line and this line, if they are parallel, that means theta equal to 0, then in that case, if theta equal to 0, that means the electric field is exactly perpendicular to the surface area. In that case, you can write down your electric flux phi, this is equal to E times A. This is the formula, okay, E times A. This is the, so electric flux again is the electric lines of force passing through the certain area. You define like a per unit area, but the lines of force, they must pass perpendicularly through the surface area. That is what we call the electric flux. Okay, so there is a law about the electric flux. We call that Gauss law. Okay, Gauss law. So the Gauss law is, let us suppose you have a charge here, Q, and one closed surface like this. This is a closed surface. Enclose this charge. This, you see that it is not regular, but it is closed surface. This is closed surface. And we know that if this is a charge, the charge is coming out of the conductor, this surface. So how? Like this. Like this. How many lines of force coming out of this the closed surface then? So the number of electric lines of force coming out, pointing out of the that closed surface is proportional to the charge enclosed by this closed surface. The electric lines of force coming out from this the closed surface, that is, you can simply write down, that is phi is equal to E times A, and this is proportional to the EA, this is proportional to the charge enclosed by that closed surface. The E times A, what is this? This is electric flux. Electric flux coming out from this closed surface, and this closed surface enclosed the charge Q here. So the electric flux coming out this closed surface, from this closed surface, is EA is proportional to the charge enclosed by the surface. So you can write down EA. If you want to put equal sign, you can put equal sign 1 over epsilon 0 charge enclosed. This is the Gauss law. The number of electric lines of force coming out through this surface, if that surface enclosed the charge, then in that case the electric flux coming out of this surface is proportional to the charge enclosed by that surface, closed surface. Okay, so this is the Gauss law, and this surface, the closed surface, we call the Gaussian surface. This one, this is called as the Gaussian surface. Okay, so simply the electric flux through the Gaussian surface is proportional to the charge enclosed. Okay, so this is useful to calculate the electric field. Let me give you the example. So the Gauss law is this: E times A, which is electric flux, is equal to 1 over epsilon 0. You know the epsilon 0, it is permittivity of the free space. If you need, your epsilon 0 is 8.854 times 10 to the power negative 12 coulomb square per Newton meter square. This is epsilon 0. Okay, so permittivity of the free space. Now let us apply this law. let us suppose you have a solid sphere like this. You have a solid sphere, and this solid sphere has a charge. Let's say this is the charge, positive charge. Consider the center is here. Center is here, and the radius of this sphere is, let me call, R0. Now I want to calculate the electric field here. Let me call this is point A. I want to calculate the electric field here at point A. I want to calculate the electric field outside the sphere. Let me call this is point B. I want to calculate the electric field at point B. And another point, I want to calculate the electric field right there at point C. I want to calculate the electric field at point A. I want to calculate the electric field at point B, and I want to calculate the electric field at point C. So electric field at point A, that is, let's say, electric field, point A is on the surface of the sphere, right? Look, point A is on the surface of the sphere, so you can say that the electric field on the surface of the sphere, surface of the sphere, that is point A. So the surface, you can consider this whole spherical surface, this, and we have a Gauss law. What is Gauss law? Is electric flux through the surface, closed surface. This is also closed surface. This is equal to 1 over epsilon 0, and let us suppose the charge here, this charge is simply whatever you call, you can call Q. So charge enclosed by this surface is, you can call Q. Okay. Now look at this A. What is A? A is the surface area of this spherical surface, and this spherical surface has a radius R0. So what is the formula to calculate the surface area of the spherical object? Is E, area is 4 pi R0 square, because I said the radius is R0. This is equal to 1 over epsilon 0 Q. This is a charge enclosed. So what is electric field at point A then? Your electric field at point A, this is equal to 1 over 4 pi epsilon 0 Q divided by R0 square. This is the electric field at point A on the surface of the sphere at point A. Now what about the point B? Now we can calculate electric field at point B. Point B is outside the, let's say, electric field at point B, or you can write down outside the sphere, outside the charged sphere. If you want to calculate the electric field this point here, so what you can do is you can draw the spherical surface passing through this point like this. Draw the spherical surface like this. Please try to make a sphere, okay? My diagram is not quite good. Something like this, okay? And let us suppose this radius, the radius of this, the big sphere is, let me call this is R1. R1 is the radius of the big sphere. And the electric flux to this Gaussian surface, the big one, you do the same formula, E times A. What is E? E is the electric field at point B this case. Okay, this is equal to 1 over epsilon 0 Q. Because this sphere, look at this big sphere also enclosed the little sphere there, the solid sphere there. So this big sphere enclosed this charge, Q charge. So E times A is equal to 1 over epsilon 0 times Q. But what is A then? Okay, E times what is A? A is area of this big spherical surface, this big Gaussian surface. Again the formula is same, 4 pi, but R radius is R1 this time. R1 is square. This is equal to 1 over epsilon 0 times Q. Okay. So what is E? E is 1 over 4 pi epsilon 0 Q divided by R1 square. So this is outside the sphere. This is inside the sphere. But we have another one, point C, that is inside the the sphere, charge sphere. So you do the same thing. If you want to calculate the electric field right here, you draw the spherical surface, another one, little one. You draw the spherical surface like this. I don't know if you see that. You can do. Let me use this one. Okay. You can draw this from this point. This point is C. This point is C, and you can consider this radius is, you can consider R2 then. But look at this. This little sphere here. This sphere is inside the solid sphere. How much charge do you have here? I told you the charge is always resides on the surface. Charge is always on the surface of the sphere. So look at this, the first sphere, this solid sphere, charge is on the surface of this solid sphere. But there is no charge inside the conductor. That means the yellow one here, there is no charge here. This sphere, the little one, the yellow sphere, it does not enclose any charge. No charge there. So third case, inside the charge sphere, that is, you can make, this is your second case, this is your first case. The third case, you can say that third case, electric field inside the charge conductor. Electric field inside charged conductor or charged sphere, it is better to say sphere. That is point, this point is C, point C. This little sphere, it does not enclose any charge. So charge enclosed, Q enclosed. This is equal to 0. If this is equal to 0, now look at this, the formula is, you can do that, E A, this is equal to 1 over epsilon 0, Q enclosed, okay, but Q enclosed is 0, so this is 0. If this is 0, that means electric field is 0, area can't be 0, so the electric field is 0, okay. So inside the charge sphere, electric field is equal to 0. Inside the charge sphere, inside is 0, always 0, here, inside, at any point inside the conductor, spherical charge conductor, the electric field is 0. On the surface, you have this 1 over 4 pi epsilon 0, Q, this Q is the enclosed charge, okay, Q over R0 square. Outside the sphere, you have the formula here, but inside there is no electric field, okay. So this is the one example where you can apply the Gauss law. There are many. Another one also, I can give you one more. Another one is, let us suppose you have like a charge plate like this, or any conductor plate, something like this, and this is charged, this is charged. So if you want to calculate the electric field right here, what you can do is, you can draw the surface here. This is the surface, and this surface enclose only this area here, And you know that the electric field, electric lines, of course, they are always coming out of the conductor perpendicularly. So the electric field is like this, this way. But I consider this area is equal to this area. Okay, that is how I draw. And let me call this is area, you can say area A. And here the charge, you need to calculate the charge here. So what you need to do is, I discussed in my first lecture the surface charge density. Surface charge density, this is simply denoted by sigma. This is equal to charge Q per unit area. This is how you define the surface charge density. This is charge is in coulomb and area is meter square, coulomb per meter square. That is the surface charge density. Now if you need a charge, then Q equal to, you can write down sigma times A. That is your Q. Q equal to sigma times A. Again, please don't forget, sigma is the surface charge density. Sigma is the surface charge density. And what is our Gauss law then? We want to calculate the electric field right here. So the electric field E times A, what is this equal? This is 1 over epsilon 0 times charge enclosed. Q is the charge enclosed. Q, this is charge enclosed. So you can write down what is Q. Q is sigma times A. Q is sigma times A. So if you do that, look here. E A, this is equal to 1 over epsilon 0. Q is sigma times A. Okay. This A and this A is the same area. So what is electric field then? The electric field at this point is E equal to sigma divided by epsilon 0 then. So this is the electric field. Sigma divided by epsilon 0. Sigma divided by epsilon 0. So this is how you calculate the electric field at this point. Okay. And one thing, the electric field on the surface of the conductor is always same, okay, uniform. So this is about the Gauss law. Chapter 16 is done. We have to start chapter 17. Chapter 17 is basically about the electric potential. So let us talk about that electric potential. So before starting electric potential, you need to know what is gravitational potential. You need to know what is conservative force, what is non-conservative force. In physics 120, you learn that there are two types of force: conservative force and you have non-conservative force. What is conservative force? What is non-conservative force? We did that in physics 120. Okay. So the conservative force, if the work done by the force is independent of path, that force is called as the conservative force. For example, if you release this object from here, this work is done by gravity, and work done by gravity depends on only the height. Work done by gravity depend on the height only. Initial position and final position. It does not depend on path. That it depends on only initial and final position. That means it depends on height. That is why the gravity is a conservative force. And like a friction, work done by friction force. If you have the rough surface or if you have a smooth surface, the path taken, that makes a difference. So work done by the friction force, that depends on the path. That is why the friction is a non-conservative force. So if the work done by any force is independent of path, that is called as the conservative force. And the important things you need to know here is, the potential energy is defined only for the conservative force. The potential energy is defined only for the conservative force. Therefore, we have a gravitational potential energy because gravity is the conservative force. We have elastic potential energy because the spring force is conservative force. Now here in chapter 17, we have to talk about the electrostatic potential energy. Electrostatic force or Coulomb force is a conservative force. That is why we have a electrostatic potential energy. Okay, and I am talking about the potential energy, but what do you know about the potential energy? Energy due to the position of an object. Okay, so if you would like to know the example here, like a conservative force is gravity is a conservative force. Gravity, like spring force, you can write down Coulomb force, they are conservative force. Okay, non-conservative force, simply you can write down friction here. Friction, they are non-conservative force. And again, the potential energy due to the position of an object. Let me quickly remind you. Let us suppose this is the ground, and you have one object. This object has a mass m. Okay, this is initial position of an object. So this object has an energy. You know that the potential energy, I am talking about the gravitational potential energy, it is the height dependent. And I measure the height from here. So here you have an initial potential energy, PEI, and if you release from here, so right there, you have a potential energy, PE final. Okay, so if you get the difference, PE final minus PE initial, what is this? This is your change in potential energy, delta PE. Change in potential energy, delta PE, that is equal to negative work done. Here, if you release this mass, the work is done by gravity. And the change in potential energy, delta PE, that is the negative of work done. Because you can see that the final potential energy here, it is 0, height is 0. Initial potential energy, you know the formula is potential energy, this is equal to mgh. So here you have a certain potential energy, here you have a 0 potential energy. So if you get the difference, you get the negative. So now let us apply the same concept in chapter 17, where we have to talk about the electric potential and electrostatic potential energy. Okay, and again the Coulomb force or electric force is a conservative force. It is independent of spark. Okay, let us suppose you have a two plate. You have one plate here, you have another plate there. This plate, this is positively charged and this is negatively charged. And you can choose 2 points. One point is here, close to positively charged plate. Let me call this point is A. And another point is very close to this. This point is B. Now, if you release the tiny positive charge from here, this tiny charge, but it is positive. If you release the tiny positive, this is positive charge from point A. If you release the tiny positive charge from point A, what happens? Look at this. If I release this mass, what happens? This mass is accelerating to toward the ground. I don't apply any force. I release this. Gravity is the force here. Same thing. This charged particle, the tiny one, it has a potential energy due to its position, similar to this. This eraser, it has a potential energy. Here it is a gravitational potential energy. If I release, it accelerates downward. So if I release this charged particle, what happens? This charged particle accelerates toward point B here. This is point B. So this has some energy. We call that is electrostatic potential energy. That is called as the electrostatic potential energy. So the electric potential, you can write down V. This is simply electrostatic potential energy for unit charge. That is called as the electric potential. Electrostatic potential energy, simply I can use U to represent the electrostatic potential energy. I can use U, uppercase U. So your electric potential of V, this is equal to U divided by Q. What is U? Electrostatic potential energy. So this is in joule. Charge, coulomb. Okay, joule per coulomb. This is called as volt. Okay, so the electric potential V is equal to electric potential energy, electrostatic potential energy divided by charge, and this is measured in volt, and this is a scalar quantity. Okay, now from here, if you want to calculate the electrostatic potential energy, you can easily get this formula. Electrostatic potential energy, U, this is equal to Q times potential. So simply here I use the word potential, but it is better to say potential difference, because only the difference between 2 points, the difference between the potential between 2 points, the difference of potential between 2 points, that is physically meaningful. So only the potential difference is physically meaningful. So if you just say electric potential, your reference point has, like, we consider zero electric potential energy there. We relative to the zero potential energy. Okay, so electrostatic potential energy, that is equal to charge Q times electric potential. Okay. Again, if you release the tiny charge from point A, the work is done by the electrostatic force. Similar to this, if you release this mass, work is done by gravitational force. In this case, if you release this tiny charge particle from here, work is done by the electrostatic force, or you can say Coulomb force. And work done formula, think about it. What is the work done formula from your physics 120? Work done is force times D. And in this case, let us consider the force is electrostatic force, and the distance between them is, this distance is, you can call D. D is the distance. Okay, and if you need, I told you that electric field is always from positive to negative charge, so the electric field is like this. This is the direction of the electric field. Okay, so your work done is equal to force, electrostatic force times the displacement. But electrostatic force, look, electric field E, this is equal to electrostatic force divided by Q. So your electrostatic force is Q times E. I use a definition, in my definition I use Q0 here. You can do that, Q0, but that is just the definition. So any charge work. So the electrostatic force is this. Okay, so your work done, this is equal to Q E D. This is the work done. This is the work done. But you know that here, this particle, it has a high potential energy here. Similar to this. So look, here, this object is above the ground at a height h from the ground. So here it has a high potential energy relative to the ground. Here, high potential energy. And if you start to measure from here, this is your initial potential energy. If you release on the ground, potential energy is 0. So here you have a high potential energy at this point, and on the ground you have a low potential energy. Similar to that, this position, you have a high potential energy here, and you have a low potential energy there. So the difference is, you can say that potential energy at point B minus potential energy at point A. Potential energy at point B is smaller than potential energy at point A. So this is, if you get the difference, then I already mentioned that the change in potential energy, that is delta PE, and that is negative work done. So it is negative W, but W is QED, so you can write down negative QED. So this PEB minus PEA, that is the potential potential energy, electrostatic potential energy, and that is difference, PEB minus PEA. So you can simply write down PEB minus PEA, this is equal to negative QED. Okay. So the difference of potential energy, is the work done. Okay, and now let's see. I mentioned that you can do this way. If you want to calculate the potential at point B, okay, minus potential at point A, what is this? Potential at point B and potential at point A, this is the potential difference between point A and B, VB minus VA, the potential difference between point B and point A, that is, you can simply represent by VBA. So what is this equal? This is equal to potential energy at point B per unit charge minus potential energy at point A per charge. So you can write down VBA, this is equal to VB minus VA, and this is PEB minus PEA divided by Q. Sometimes this formula is also useful. Okay, sometimes this formula is also useful. But I already gave you the formula. This is the potential difference between 2 points. If you want to calculate the potential just at a point A, if you want to calculate VA, then in that case, you can consider the one point where the potential energy is zero, So it is relative to the zero potential energy. You can do this PEA divided by Q. This is the potential electric potential at point A. But again, please don't forget the potential. The potential is meaningful if you get the difference only. The potential difference is physically meaningful. Okay, so the basic formula here is your electrostatic potential energy. This is equal to Q times V. This is electrostatic potential energy, and another formula is simply, you can write down, if you need a potential, just the electric potential is, definition is potential energy, electrostatic potential energy per unit charge. This is what you need to know. Okay. So we learn about the electric potential. We learn about the electric field. Is there any relationship between them? Any idea? Is there any relationship between them? Let us see if there is any relationship between electric potential and electric field. You know that electrostatic potential energy U, actually this is the work done, and this is equal to you can write down W. Okay, electrostatic potential energy and work done, both are in joule, they are equivalent. So what is U, what is W then? How can you plug the formula there? Any idea? You can do this. Q times V, this is equal to negative QED. Work done is negative QED. So this Q and this Q, they cancel out. So what is E then? You have a negative sign, that's why I'm write down right there, V divided by D. So the relationship between electric field E, this is equal to negative V divided by D. E, electric field, this is equal to negative V divided by D. Sometimes this formula is also useful. Okay, so electric field E, this is equal to negative V divided by D. We call this term V divided by D, we also call that potential gradient. Okay, potential gradient. So you can see from here the negative of potential gradient gives you the electric field. The negative of potential gradient gives you the electric field. Okay, and there is one small topic, we call that equipotential surface. Equipotential surface. You can have an equipotential line also. Equipotential line, equipotential surface. So what do you think? What is equipotential surface? EQ means equal, potential means of course the potential. So that means the surface having equal potential everywhere. Now if you consider this board like this point, this point, this point, this point, everywhere, you measure the potential here, here, there, everywhere. If you measure the potential and if you get the equal number, equal potential, then this surface you can call the equipotential surface. Okay, for example, so the surface having equal potential everywhere. So if you have, let us suppose this is a equipotential surface, everywhere you have the same potential. Let us choose one point is here, another point is there, and I said this point is equal, this surface is equipotential surface. So how do you calculate the work done to go from A to B? What is potential difference between A and B? Zero, because they have the same potential. Potential here and potential there is equal. So potential at point A and at point B, they are equal. So if you get the difference, the potential difference is zero. So if the potential difference is zero, no work is done there. Okay, so if you have the equipotential surface, no work is done there to move the charged particles there. So equipotential surface, the surface having equal potential. For example, let me draw something like this. Let us suppose you have a little charge here, Q, and you see this is the sphere. This is the sphere. Let us consider this is radius R1. If you want to calculate the potential right here, let me call point A. If you want to calculate at point B, at point C, at point D, everywhere, calculate the potential at point A. What is this? To calculate the potential, like this is a really small charge, point charge, the potential due to point charge V, this is the potential due to point charge, this is equal to K, this is the formula, K Q divided by R. This is the formula to calculate the electric potential due to point charge. If necessary, we can derive this formula also. This is the potential, electric potential, KQ divided by R. This is due to point charge like this. I have a point charge here, small charge, okay, and I want to calculate the potential at point A, at point B, at point C, at point D, everywhere on this surface. But it is a sphere, okay. So if I calculate here, what is this? This is KQ divided by R, potential at point A. What is potential at point B? What is VB then? Same thing, KQ divided by R. Here, VC, same thing, KQ divided by R. Sorry, uppercase, R. So look, everywhere you have the, if you are talking about this spherical surface, everywhere you have the same potential. Because K is a constant, Q is same for every point, R is also the same because this is spherical surface. So this surface, this surface is an equipotential surface. This is equipotential surface. Similarly, this surface is also equipotential surface. This is also the sphere. This is also the equipotential surface. This is also the equipotential surface. If you calculate the potential here, there, everywhere, you get the same potential. That is why this is equipotential surface, this is also equipotential surface. And the one important property is, if the charge is moving in equipotential surface, no work is done there because there is no potential difference. No work is necessary. That's the one point. And the second point is, DC is considered like DC is equipotential surface. If your electric field is this is the direction of electric field E. Equipotential surface right here. If you draw the tangent here, this is 90 degree. The equipotential surface and electric field, they are perpendicular always. Okay. Same thing here also. If you draw the tangent, this line, the tangent line and the electric field, they are also perpendicular. So you have to say that the electric field and equipotential surface, they are perpendicular, or electric field and equipotential line, they are also perpendicular. Okay. So my video is almost hour long, so I cannot make longer than an hour. So I want to stop here, then I'll bring another video. Okay, thank you.